Hi guys, I'm trying my first video myself. See if I can get this into focus. Okay, there we go. We are continuing on with the gradient function. If you remember right, the gradient function is finding the slope of the line or the gradient of the line at any point on a curve. We figured out already that instantaneous rate of change happens when you have a curved graph and not a linear. So there's something called the power rule. This is the power rule. And what the power rule is a shortcut for us to write the gradient function. What we're talking about is this would be the original function that creates the graph, whether it's a parabola, a cubic, whatever. We would need a different function to figure out what the slope is of any point on that function. So the gradient function is actually a function that is based on the x-coordinate of a point on a curve. We're going to go through right now and figure out the mechanics on how to use this, and then we're going to actually apply it. So let's get started. We first have a few examples, and these are all in chapter 6 in your book if you're interested. And we have a couple of names. If you, hold on a minute. If you have a function that starts out as a y equals, and that's how your original function is named, the most common way then to name the gradient function is dy over dx. Now we have a different name because it's a totally different function. They don't look the same, but they are related. If you have your original function named f of x, the gradient function is f prime of x, and that prime is the apostrophe. So I'm going to go through some examples just to get you familiar with it. My first example is y equals 6x to the third. That is my original function. So now what I want to do is I want to create my gradient function. So I'm doing a totally different function. And as you can see, this original function is named y. So most common, and you'll see more than one ways to do it, but most common to name the gradient function, we're going to say d of y over d of x. And this just means a change in y over change in x. And what you got to keep in mind is gradient means slope. So this formula here is saying it is a slope function. Now let's go through this. In this case here, n is equal to 3 and a is equal to 6. So if you look at how we're going to write the gradient function, this na means n times a, and then there's also an n up there. So here's how it works. You say n, which is your exponent, times a, which is your coefficient. So 6 times 3 is 18. And then you still have the variable because the gradient function is a function of the x variable. Original n was 3, but from that it says minus 1. So we did n times a, that's what this says, n times a. And then from n, we're going to subtract 1. And now let's just simplify it. So d of y over d of x equals 18x to the second. And that is your gradient function. Now, how would you use this? Well, say this is going to be a curve of a cubic. Say it's a volume of a container. And I want to know what volume would be at x equals 3. Well, I could plug 3 in here, and I'd find out what the rate of the volume would be at that point. Now that explanation was not very good, so we're going to go on. And let's do this again. Our n is 4, and our a value is 1. And looking at the derivative, we have again y equals, so let's name our gradient function. If I use the word derivative, it's the same thing as using the power rule and the word differentiation. So now it says take your n, which is 4, multiply it times your coefficient. So 4 times 1 is 4. With the variable x, that was our original exponent, and then it says subtract 1 from your original exponent. Move my camera. So what you have is d of y over d of x equals 4x to the third power, 4 minus 1. Okay? Let's look at this one. Y equals x. Well, n, what is our n? What's x? It's really x to the power of 1. So n is 1, and a is 1. So this is, again, our original function is named y, so we're going to name our gradient function d of y over d of x. And again, we're going to multiply n times a, which is 1. Then you have x, the original exponent, minus 1. It's always the same process. N times a, the exponent times a coefficient, and then subtract 1 from the exponent. So let's clean this up. X to the 0. Remember, anything raised to the power of 0 equals 1. So in this case, our derivative is 1. Notice, that's a constant number. There's no x value. And if you look at the original function, y equals x, and you were to graph it, this would be a line. This would be a graph of the line that looks like this. And that graph will have a constant function. And in slope-intercept form, we would say that the slope of the line is 1. And we'd know that. And so we use the derivative to differentiate our linear function, and we proved that, okay, the slope in this case is a constant 1, no matter what point of the line you're on. Let's go through a few more. Here you have y equals, you know how I hate having it turn, there we go. Okay, here you have y equals 1/2 x to the power of 2. So our n is 2, our a is 1/2. The function is named y, so let's name it d of y over d of x for the gradient function. And do the same process. The exponent times a coefficient. What's 1/2 of 2? The answer is 1. X raised to the power of 2, but remember you've got to subtract 1. So let's clean it up. D of y over d of x equals x to the power of 1. We typically don't leave it that way. We would just write equals x. And that's it. Okay? Let's go on to this one. I paused because I thought I did something wrong, but it's fine. I didn't. Okay, this original function is y equals 7. Now, I don't see any variable here. But you know what the variable really is? X to the 0 power. Remember I said over here, anything raised to the power of 0 is 1. So 7x to the 0 power is the same as 7. So let's do the same thing again. Let's name our gradient function. Do the same process. You take the exponent times a coefficient. 7 times 0 is 0, so guess what? You just put in 0. And it's 0 because this is a constant. This graph looks like this, y equals 7, 1, 2, 3, 4, 5, 6, 7. It has a 0 slope. So doesn't that make sense? Our gradient function tells us the slope. Well, it has a 0 slope, so our gradient function proved that the slope was 0. Let's do this next one. Again, it's a y equal, so I'm going to name it d of y over d of x. And by the way, sometimes you'll see y prime. That also works. But it's up to you. I just don't want you to get confused when you see anything. Okay, so this is n equals 9, a equals -7. Here I forgot to say n equals 0 and a equals 7. So you do the power rule again. 9 times -7 is a -63. Your x, of course, stays there. And then you have your original exponent and you subtract 1 from it. So the final answer is d of y over d of x equals -63 x to the power of 8. And that's your answer. So those were 6 examples with functions named y equals. I just want to, and also they each only had one term in the function. I want to go over what happens if you have functions with more than one term. So let's look at that. Well, here's our original function. F of x equals 9x minus x to the 11x to the third power. Because it's f of x, I'm going to name this f prime x. Prime is a little asterisk. I need that to let you know that this is a different function than our original. And that should tell you it's a gradient function. So now we have two terms, 9x and negative 11x to the third power. We have to differentiate twice. So let's look at this first one. This first term, n equals 1 and a equals 9. So let's do that first. You have 1 times 9 is 9. X raised to the power of 1 minus 1. Okay. Now our second one here, we have n equals 3, and a equals negative 11. So again, 3 times negative 11 is a negative 33. X, the original exponent of 3, minus 1. So now let's simplify. F prime x equals 9x to the 0 power, we'll clean that up in a minute, minus 33x to the second power. And what I say by cleaning it up, I want to simplify. We never say x to the 0. X to the 0 means 1. So 9 times 1 is 9 minus 33x squared. So this problem is different than the prior 6 we did for two reasons. One, I'm using a different notation, f of prime. And then I'm also having to differentiate not only one term, like the previous functions, but two. So let's do another one. F of x, so let's name it f prime of x. Now we have three terms, so we have to do the same thing. The n in the first term is 4, and the a value is 1. I'm going to write it up here. I think you can see it. A equals 1. That's the first term. The second term, when you do not see the exponent, you know that it's 1. So in this case, the a is 3 and the n is 1. Then this last term, 2, it's really 2x to the power of 0. So you have a is 2 and n is 0. And now we've got to differentiate 3 of these. So let's do the first term. The exponent times the coefficient is 4. X, the original exponent was 4, and we're going to subtract 1. The second term, 1 times 3, the exponent times the coefficient is 3. Here's your variable x, and then we have the original exponent of 1 minus 1. And the last one is 0 times 2, and as soon as you see that, well, what's 0 times 2 is 0. So now let's simplify it. F prime of x is equal to 4x to the third, that's 4 minus 1, plus 3x to the 0 plus 0. Let's simplify it one more time and clean it up. 4x to the third is fine, but 3x to the 0 is 3 times 1, so we just leave it at 3, and you can drop the 0. And the last example looks totally different. You cannot apply the power rule until you expand this out into something like either a binomial or a trinomial. So the first thing we have to do is put the original function in a form where you can apply the power rule. So I'm still looking at the original function, y equals. Notice I did not make that a gradient function yet because I have to distribute this. So x times 2x is 2x to the power of 2. X times 3 is 3x. Now I can say, let's differentiate. And this one, I'm just going to do it without saying anything. And you can slow this down if you want to take notes. It's plus 3, x to the 1 minus 1. And we're going to simplify. And I skipped a step. I would have put 1 here because 2 minus 1 is 1. And I would have put x to the 0 here, but I think you guys have got it. And that's all we're going to do this week, is to apply the power rule. But the problem I have with doing that is you're saying, well, so what? What does this mean? So I want to show you one word problem so we can understand what a gradient function does. Okay, so let's go to this example. And if you're with me on Thursday, this example will look familiar to you because this is the one that I used. So I'm calling this differentiation in action. Okay, so say you have a toy rocket. When you shoot it up from the ground, it follows a parabolic trajectory. And after t seconds, the vertical height of the rocket above the ground in meters is given by this function. So this function, h of t equals 37t minus t squared, is what determines this parabola. That function looks like that on the graph. Now let's look at that. That is a function. This function here tells us the height of the rocket is based on the number of seconds in the air, number of seconds passed. So if I want to know at this point here, 10 seconds passed, that means that's my t. So I want to interpret what this graph shows. This says 10 to 70. So at 10 to 70, what that means in words is that at 10 seconds, the height of the rocket is 270 meters high. Okay? Notice 10 to 70 is what we would have gotten if we had substituted 10 for t in this equation, and that would be our outcome. And likewise, how high is the rocket at 28 seconds? So at 28 seconds, the height of the rocket is, what does it say, 28, 252, is 252 meters high. So the original function is a function of the height of the rocket and the time. But what I want to know is how fast is the rocket going at 10 seconds? How fast? So I want to know the gradient. What is the gradient at 10 seconds? And now that's where you're going to use the gradient function. So to do that, to answer the question, find the speed at 10 seconds and find the speed of the rocket at 28 seconds, we're going to use the original function. And that original function, that tells us the height of the rocket based on the time. The gradient function, h prime of t, here you have n equals 1 and a equals 37. That's one of the terms. The second term in this function is n equals 2 and a equals -1. So let's differentiate by using the power rule. We're going to take the 1 times the 37, which is 37t. Original exponent was 1, so we subtract 1 from that. Now we have 2 times a 1, -1, is a -2t. The original exponent was 2. You subtract 1, and let's simplify that, and then we're going to use it. So the gradient function is h prime t equals to 37. 1 minus 1 is 0, so t to the 0 power is just 1. and this is 2t, t minus 1, 2 minus 1 is 1. This is the gradient function. This tells you, I can tell how fast the rocket is going based on the time that's passed. So in this case, if I want to find the speed of the rocket at 10 seconds, I'm going to say, okay, speed, this is gradient. This is my gradient function here. This is my speed, so I'm going to use my gradient function. And it's based on my t value. So my t here is 10. So we're going to say at 10 seconds, how fast was the rocket going? So use your gradient function, 37 minus 2, and instead of t, we're going to substitute 10. And now it's just a matter of simplifying. So the speed of the rocket is 37 minus 2 times 10, which is 20. So we get 17. The speed, now I'm capitalizing it. Remember, this tells you speed, rate of change, instantaneous rate of change. The speed of the rocket at 10 seconds is 17 meters per second. And that's the difference between the original function and the gradient function. The original function tells you, based on the time passed, how high is the rocket. The gradient function tells you, based on the time, at that time, how fast the rocket is going. So let's finish this up. And this is not an ordered pair. This is the rate of change or the speed. So again, to find the speed, that means use the gradient function. And in this case, your time that passed is 28. So use the gradient function. And the number we're putting in there is 28. So h prime of 28 is equal to 37 minus 2 times 28. 28 times 2 is 16, looks like 56, okay. 37 minus 56, because 2 times 28 is 56. And 56 minus 37 is a 9. That's a 4, it looks like 19. So the speed of the rocket is 19 meters per second at 28 seconds. I like how I said it better for 10 seconds because it was less confusing. But anyway, this was just a brief introduction as to what is the difference, what is a gradient function? Gradient function is a function that you can use to find the instantaneous rate of change based on the x coordinate of the original function. And that's it.